Have you ever thought about that little piece of metal holding up your grocery list? It sits there on your fridge, silently pulling on the steel beneath it, without a battery, a wire, or a single drop of fuel. So what exactly is doing the heavy lifting? Is there some hidden well of energy trapped inside, or is this an illusion of physics? That invisible pull might seem simple, but it is the exact same physical mechanism that guided the first explorers across the oceans, and it serves as the engine powering nearly every piece of modern technology we rely on. To understand how we harness this force, we have to go back about 2.5 millennia to ancient Greece. Legend has it a shepherd named Migas was walking across a hill when the iron nails in his shoes suddenly clamped down against the earth. What he stepped on was this, a dark metallic rock called Lodestone or magnetite. It was the world's first natural magnet. The Chinese civilization eventually figured out how to shape this material into tools, resting a spoon-shaped piece of lodestone on an ancient bronze plate to create the world's first navigational compass. That single invention allowed humanity to navigate the open oceans safely. Yet, for centuries, people crossing the globe had no scientific explanation for how it worked. To them, it was magic. The shift from magic to science happened in 1600, when English scientist William Gilbert published this foundational text, De Magnet. He proved that compasses point north because the Earth itself is a massive magnet. Look closely at this grid of iron atoms. In normal metals, tiny magnetic domains point randomly, canceling their forces. But in ferromagnetic materials, these domains seamlessly snap into line. Pointing exactly the same way, they project a unified, invisible field. Magnetism is the raw physical power of billions of microscopic atoms acting in perfect unison. In the 1820s, scientists uncovered a mechanical link that triggered an industrial boom. Hans Christian Ørsted noticed that running an electric current through a wire actually generated a magnetic field around it. Shortly after, the man in this portrait, Michael Faraday, proved the exact opposite. Moving a magnet near a wire could generate an electric current. This mutual relationship meant that physical motion could be turned into electricity, and electricity could be turned into physical motion. That single principle gave us the electric motor and the generator. Electricity and magnetism are essentially two sides of the same coin, giving us the ability to synthesize artificial power on demand and run machines of any size. By the 20th century, we pushed this relationship to the extreme with rare earth materials, creating neodymium magnets capable of holding hundreds of times their own weight. Building these requires serious factory engineering. Raw neodymium, iron, and boron are mixed in precise ratios and then melted down in high-heat induction furnaces. The hot alloy is quickly cooled, crushed into a superfine powder. But the dust is completely dead. The atomic domains are entirely random. To wake it up, powder in a mold is hit with a huge magnetic field, forcing particles to snap into uniform alignment. Then, sintering. The powder is heated until it fuses into a solid block and coated to prevent shattering. What starts as raw earth and random dust is forced into atomic perfection, resulting in the high-grade supermagnets needed to operate heavy industry. Look at this massive crane head holding thousands of kilos of scrap steel. Turn the current on, it grabs the weight. Cut the power, and the steel instantly drops. That exact same physical principle also offers life-saving precision. The extreme magnetic fields generated inside an MRI machine like this one allow doctors to peer straight through human tissue without making a single surgical cut. And it is remarkable how rapidly we evolved from the bulky, rudimentary early prototype you see here into the sleek medical scanners used in hospitals worldwide. We've even applied this force to transportation. By utilizing magnetic levitation, the train scene suspended above its tracks here glides with almost zero friction, safely hitting speeds over 600 kilometers per hour. As we look for new ways to generate clean energy, we rely on heavy-duty supermagnets placed right inside the housing of massive wind turbines like the one being assembled here. Whether we are moving people, diagnosing illness, or generating power, these invisible fields serve as the core physical infrastructure of our era. Of course, manipulating fields this intense carries risk. Modern supermagnets are so strong, they can easily wipe data drives, disrupt pacemakers, and cause lethal internal injuries if accidentally swallowed. We treat them with strict caution in industry, yet we also live alongside them every day, in the speakers of our headphones, the motors of our ceiling fans, and simple decorations on our appliances. So the next time you stick something to your fridge, remember you are interacting with an invisible miracle of physics, the exact same atomic alignment that guides our ships, spins our turbines, and keeps the modern world in motion.